You're welcome to this YouTube channel of mine. It's your teacher again. I've come to take you through what we call moral concept and stoichiometry. So stay tuned to the end of the video because there are many things I'm going to simplify in this topic. So if you have any problem with moral concept, sit down and watch this video. But first, subscribe and also like the video. Tap the subscription button just below the video here. Let's dive into this without wasting of time. Now today in this moral concept and stoichiometry, I'll discuss the following. I'll discuss the mole, just a brief highlight on what's a mole, but we shall dive into more of it when I'm handling moles in part D here. Then I'll also look at relative formula mass. How do you get the relative formula mass? Of course, it comes from the word formula, so that will refer to a compound. Then look at what we call percentage composition. How do you get percentage composition? Then empirical formula and molecular formula. Then we dive into how do you find the moles. Then we dive into using chemical equations to work out moles and the masses and also volumes of gases. It's what we are calling stoichiometry, relating reactants and products through a chemical equation. So lastly, we shall look at volumes of gases at standard conditions of RTP and what we call STP. So let's start on what is a mole here before we can follow on other parts here. Now we are starting with what's a mole. So a mole, let's pick it from here. Let's write here the symbol of sodium. Sodium is 2311. Now by observation, sodium is weighing 23 grams here as its weight here. So what does 23 grams mean here? We call this one atomic number. Then we call this one atomic. This is called atomic mass. This is called atomic number. Sorry for that. Atomic mass, atomic number. Now the word atomic mass refers to the mass of what we call the mass of 1 mole of atoms of sodium. Then what could a mole be? Now to understand a mole, we will just relate it to the mass of sodium to understand a mole. So a mole of sodium is actually equivalent to the atomic mass of sodium. So to understand a mole, we just understand the mass of each element and that will be equivalent to the mole. So the mole is actually equivalent to the relative atomic mass of the element. And normally a mole of any substance, always in terms of particles, in terms of masses, it's equivalent to its atomic mass, to its relative atomic mass. Then that substance in terms of its mass normally has certain number of particles which we call the Avogadro's number. So a mole of a substance is actually the amount of a substance that is actually containing a certain number of particles, which is exactly 6.02 times 10 power 23 particles. So we are saying that a mole of a substance, which is actually its relative atomic mass, the mass of its atoms, is a mole of a substance is the amount of a substance containing 6.02 times 10 power 23 particles. So particles of a substance can be ions, molecules, or atoms. So we are saying that the mole of a substance is the amount of a substance which can be its weight, but that weight must contain these particles. So we say the weight of 1 mole of sodium atoms actually is actually equal to its relative atomic mass, which is equivalent to this number of particles. So if we go on the weighing scale and weigh 23 grams of sodium, we would have exactly 1 mole of sodium. For magnesium, magnesium has 24 as its atomic mass, relative atomic mass. If I weigh the 24 grams of magnesium, what will I be having? I will be having 1 mole of sodium magnesium atom. If I weigh aluminium is 2713. If I weigh the 27 grams of aluminium on a weighing scale, it's actually what I'll be having as 1 mole of aluminium atoms. So a mole is actually what you understand by in terms of the weight of a substance as its relative atomic weight, or in terms of the particles of aluminium in exactly 27 grams are always equal to this number 6.02 times 10 power 23. So that's a small introduction about a mole. Now let's dive into, we are going now to exhaust this part of a mole in the next few minutes, but let's exhaust what we are calling actually calling the relative formula mass. This area is quite big, so I'm moving a bit swiftly. Now, to understand relative formula mass, we need to first also understand what we call relative atomic mass. So this is called RAM, whereas this is called RFM. So RFM, by understanding RAM, you understand RFM. Now, to understand the relative atomic mass, I've just been explaining that that's actually what you always see on the upper number here called the atomic mass. Atomic mass is 23 grams here. Then the relative atomic mass, having the word relative makes it use the units. So the relative atomic mass is actually equal to the atomic mass of a substance but without units. So what's relative atomic mass? It's just the mass of 1 mole of atoms of an element. Of course, even the atomic mass, 23 grams, is the mass of 1 mole of atoms of an element called aluminium. So relative atomic mass is actually referring to the mass of 1 mole of aluminium atom, not 1 aluminium atom, but 1 mole of aluminium atoms is actually the relative atomic mass. So relative atomic mass is the mass of 1 mole of atoms of an element. Then the relative formula mass actually would be now referring to the formula. Formulas are for compounds. So when I determine the mass of 1 mole of molecules of a compound, or 1 mole of all the atoms found in a compound, I'm actually determining what we call the relative formula mass of that compound. So to get the relative formula mass is the mass of 1 mole of the molecules or atoms that are found in a compound. So to get the relative formula masses, we normally add the relative atomic masses of the different atoms found in the compound. Say for example, calculate the relative formula mass of zinc nitrate. Zinc nitrate. Now zinc is 65, nitrogen is 14, oxygen is 16. Now when they ask for the relative formula mass of zinc nitrate, they are simply asking for the mass of 1 mole of zinc nitrate. What mass of 1 mole of all the atoms found in zinc nitrate. So let's find the mass of 1 mole of all atoms in zinc nitrate here. So we have to write down the chemical formula of zinc nitrate. So RFM of zinc nitrate, that will give us 65 plus nitrogen is 14 times 2 plus oxygen is 16 times 3 times 2, which is actually punching there 65 plus 14 times 2 plus, that gives us 189. So you don't put units because it's relative. In case it was determine the formula mass without the word relative, you are free to put units there. So let's dive into the next. I hope you understand now how to work out the relative formula mass. I'm diving into now what we call the percentage composition here. So let's start the other part called percentage composition. Determine the, so just have a small formula. Percentage composition is equal to mass of the element, just have here mass of the substance over mass of the sample. So the sample times 100 here. So let's dive into one example here. Calculate the percentage of oxygen and of water of crystallization in iron 2 sulfate heptahydrate. So now to calculate the percentage of oxygen and that of water, we need first the mass of the sample, which is actually the relative formula mass of the whole sample. So the first very step, I'm looking for the RFM of iron 2 sulfate heptahydrate. RFM of iron 2 sulfate heptahydrate. Check on my video how to write these chemical formulas. When they say hepta means 7, hydrate means water, so we add 7 water molecules to it there. So is equal to, iron is 56, put that in the question. So iron 56, sulfur 32, oxygen 16, hydrogen 1. So RFN of iron 2 sulfate dot 7 water is, iron is 56 plus sulfate 32 plus oxygen is 16 times 4 plus 7. 7 multiplies hydrogen is 1. And 1 times 2, then 7 times 16 for oxygen, which is, so that's 56 plus 32 plus 16 times 4 plus 7 times 2, then plus, giving us about 278. 278, don't put units here. If you want to put units, use the word molar mass or molecular mass. So let's now look at percentage of oxygen. So I'll leave the mass of oxygen only. Now we can realize that in this sample, oxygen is appearing 4 atoms, then plus 7 atoms here, total 11 atoms. So mass of oxygen, I have about 11 atoms times each oxygen is 16. Not 11, yes, this is 7 oxygens plus 4, that's 11 times 16. Gives us, we punch in here, times 16, we get 176. So percentage of oxygen, we just have 176 out of the RFM of the entire substance, multiply by 100, so divide that by 278 times 100, we get right away 63.31%. Now let's look at, it also wanted the percentage of water of crystallization. So let's look at mass of water. Can look in the formula. Water, there is 7 water molecules, so it will be 7 times 1 plus 7 times 16, or 7 times 18. So that will be 7 times 18, giving us 126. So percentage, composition of water, that of 126 divided by 278 times 100, that gives us divided by 278. That is 45.33%. So that's how you get the percentage composition of elements or molecules or atoms found in a certain compound. So let's look at this time. Let's go to another thing here called the empirical formula and molecular formula. So diving into that, formula and molecular formula. Now, how do you get empirical formula and what is it? So, empirical formula and molecular formula. Molecular formula. Now, empirical formula is a formula which shows the simplest number. Empirical formula is a formula that shows the simplest ratio of atoms of different elements present in a compound. So the simplest ratio, that means not the exact ratio. The molecular formula is the formula that shows the actual number of atoms of different elements present in a compound. So it shows the actual number of atoms. So for example, you can have a formula HO, but if multiplied it by 2 it will give H2O. So this formula is called empirical because it's just showing the reduced ratios of the actual formula. So this is the actual formula called hydrogen peroxide. This is the formula which just shows that we need to multiply by a factor to get the actual formula. So this HO is simplest formula. H2O2 is empirical formula. So we multiply the empirical formula by a certain degree to get the molecular formula. So we shall have it like this. Empirical formula times n must give us the molecular formula. And remember, the molecular formula on calculating gives us the molecular mass. So it shall be equating to molecular mass to be arriving at the molecular formula. So we'll multiply empirical formula times the value equate to molecular mass, then solve for the n. N is the whole number to be used that relates empirical formula to the molecular formula. So let's now dive into an example here. How do you get empirical formulas of different compounds and their molecular formulas? I wanted you to keep note that molecular mass is equal to vapor density times 2. Also keep that in mind. Because sometimes they can give you vapor density, molecular mass is vapor density times 2. So have that in mind first as we move on. Let's now look at the first very example here. The first very example here. So example 1. Now, how do we arrive at the empirical formula? We normally use the experimental data. You'll see it in in the next video there within the same discussion here, how empirical formula can be determined. Now let's move on with the calculation first here. So, first question, you can have an example, hydrocarbon X. Hydrocarbon X contains 80% carbon. Determine part A, determine the empirical formula of X. Empirical formula of X. Then part B, given the molecular mass of X at 30, calculate the molecular formula. The molecular formula of X. Let's dive into that. Now to get the empirical formula, punch in here right away. So let's move. So let's start with part A. Carbon is 2, hydrogen is 1. So part A. Now the first part we have to establish what's the hydrocarbon. The hydrocarbon is a compound consisting of carbon and hydrogen atoms. So the question has only given us carbon, so I need to get hydrogen. Percentage composition of hydrogen. Composition of hydrogen. Can use H on the whole word, but don't use H2. Hydrogen, that's 100 minus 80, gives us 20%. So go into our table, and list the elements. Go into our table and list the elements. So, the elements we have carbon and hydrogen here. So we can look into our question. Carbon is 80%, hydrogen is 20. So this percentage composition, Then the next step is to establish the moles. Here we divide by the relative atomic mass. Divide by relative atomic mass. Relative atomic mass of carbon is 12. So this is 8 out of 4, spent out of 1. Let's divide. So 80 divided by 12, we are getting about 6.667, round 3 digits or more. So this will be 20.00. We add the zeros together for the decimal places to be the same here. So now by doing so, next step we get what we call mole ratio. Mole ratio we divide by the smallest, divide by smallest. So our smallest is 6.67, divided by 6.67, 20.00, divided by 6.67. So here we get 1. So 20 divided by, we get 3. Get 3 here. So you round the whole number depending on the values you have obtained. So our empirical formula will be C1H3. So let's check on here. Side. So right away there, empirical formula is CH3. Let's now look at the molecular formula in part B. So we are going to acknowledge that this empirical formula times n must give us the molecular mass. Then we solve for that n there. So carbon is 12 times N plus hydrogen is 1 times 3 times N gives us about 30. 15N is equal to 30. 15 out of 15N will give us roughly 2. So set 3 times 2 gives us C2H6. So this is the molecular formula. Come and conclude here. Molecular formula is C2H6. Now, let's instead punch into here something else here. Let's send these digits at a 2.7, at a 2.5. Then we modify this to this number, called number 2. So, given that the vapor density and density of Q, so this has Q is 29. So let's go back here. So the composition of hydrogen, we clear off this table. So percentage composition of hydrogen will be, is 100 minus 82.5. So that gives us 100 minus 82.5 gives us 17.5. 17.5, 82.5. So let's divide 82.5 to 12.5 out of 1. That gives us 82.5 divided by 12. I hope we get 6.875, 17.500. So let's further divide by the smallest in this step, 6.875, 17.500 out of 6.875. This gives us 1. 0.5 divided by there, so it's giving us 2.545. So always check this first digit before you proceed. Every calculation, especially on the mole ratio step, check this first digit. If it's a 0.5, we round first decimal place, then multiply by 2 first to get a ratio of this. Hope you understand that step there. Don't round off if it's a 0.5. Get it right there. So the empirical formula would be just plain from here to avoid overwriting. So this is going to give C2H5. Now, since the question gave me vapor density and wants the molecular formula, I'll first work out the molecular mass. So molecular mass is equal to vapor density times 2. So that's 29 times 2 giving us 58. So I bring in my empirical formula here, times N gives us 58. So carbon is 4 times 2 times N plus 1 times 5 times N gives us 58. So this is that's about 59. N is equal to 58 out of 59, out of 59, N is 2. So go back to the formula, C2, H5 times 2 will give us 2 times 2 is 4, 2 times 5 is 10. So molecular formula is C4H10. So that's how you calculate the empirical formula and the molecular formula. Now allow us to go to the next subtopic called moles. So how do you handle moles? Let's dive into that very, very fast. How do you handle moles? How do you handle moles? We are in mole concept. In the middle we are going. So how do you handle the next discussion is moles? We say now a mole is actually the amount of a substance containing 6.02 times 10 power 23 particles. So That means the mole is always representing the number of particles. But again, we say somewhere that the mole is actually the mass either called the relative atomic mass. It is equivalent to the relative atomic mass, or it is equivalent actually to the relative formula mass in case a compound. We say if you have first 23 sodium here, the mole would actually be 23 grams. The mole would be containing or weighing 23 grams, but in terms of particles it would be 6.02 times 10 power 23. Now let's dive into some examples there. We are going to about 3 or 4 different kinds of examples there. Then we put about 4 questions here. We dive into them. Then, so question 1 is calculate the number of moles in 4 grams of sodium hydroxide. And question next here will be determine the mass of 0.5 moles sodium carbonate decahydrate. The next question will be here: how many molecules are found in 0.44 grams, 0.88 grams of carbon dioxide. Then the last question would be, find the mass contained in 3.01 times 10 power 15 ions. 15 ions of find the mass contained in this drug 15 times of hydroxide ions in hydroxide sodium hydroxide. Let's have those numbers discussed. So yeah, sodium is 23, hydrogen is 1, oxygen is 16 there. Here sodium is 23, hydrogen is 1, oxygen is 16, carbon is 12 here. So diving into this, carbon is 12, oxygen is 16 here. Now let's punch in that very fast here. So you are ready with the calculator. Now calculate the mass, the number of moles in 4 grams of sodium hydroxide. Now we understand that the question has given us a mass, so we need a mass from somewhere. So we need the RFM of sodium hydroxide. RFM of sodium hydroxide is, so the sodium is 23 plus oxygen is 16 plus 1, which is exactly 40. So if you want to put 40 grams, call this one molar mass. So we discussed earlier that relative formula mass is the mass of 1 mole of molecules or 1 mole of atoms that are found in that compound. So the mass of 1 mole of sodium hydroxide molecules is actually 40 grams. So this corresponds to 1 mole of sodium hydroxide. Yeah. So keeping in mind always the RFM or the RAM is for 1 mole of that substance we are talking about. So this will be 40 grams. You start from what you have. We can't say 1 mole weighs this because I don't have moles. I'm looking for moles. So I have to say the 40 grams of sodium hydroxide, you start from what you have, contains 1 mole. We agree that 1 mole is always in the RFM or the RAM. So out of the 4 grams, you can go to a step of 1, but to save time and space. Contains, so I cross multiply here, 4 times 1 out of 40 moles. That roughly giving you 0.1 moles. So those are the moles that I wanted, but I want us to think about this. That number of moles is actually being got from the mass out of RFM. So you can build the formula there and claim that we can claim that mass is actually the product of moles and RFM. So mass is moles times RFM, moles is mass of RFM, RFM is mass of a mole. So you can play with that formula as you want to prove your answers. Let's go number 2. Determine the mass of 0.5 moles of sodium carbonate hydrate. The question wants mass, so I need to get the RFM there. So RFM of sodium carbonate, deca means 10 water. So let's punch in the value, that's 23 times 2 for sodium plus 4 plus oxygen is 16 times 3 times 3, then plus 10 times 18, the whole lot is 18, which gives us about 26 there. So this 4 is 6 plus 4 plus 4 8 plus 1 yeah? So that is 286. So 286 always has 1 mole. That should be paid attention to. So we are going to start with moles since I know moles. So I'm not going to say 286 contains 1 mole, no? Because I want mass, I have to start with moles since they have given me moles. So I will say 1 mole of sodium carbonate decahydrate. If you are worried that you write a wrong formula, please complete the whole statement. Weighs or contains 286 grams. So out of the 0.5 moles in the question of sodium carbonate, because of space I have tried this short form, weighs, we cross multiply right hand 0.5 times 286, cross multiply and divide. So that will give you the grams, which is times 0.5, which is actually 143 grams, 143 grams, which is, so that's it, 143 grams. I hope you get that right. So that's how you punch it. Even this formula could work for you. You just get more, mass is moles times RFM, which is exactly here, 0.5 moles times 486, which is the RFM. Now let's look at this, how many molecules are found. This is asking for molecules. Remember we said a mole is the number of particles. A mole is the amount of a substance containing either 6.02 times 10 power 23 molecules or ions or atoms. So let's understand here that Avogadro's number, Avogadro's constant or Avogadro's number is actually the number of atoms or molecules or ions that are found in 1 mole. So this corresponds to 1 mole. Right? The RFM was corresponding to 1 mole. So the Avogadro's number corresponds to 1 mole. That should be paid your attention there. So now, how many molecules are found in this mass? So the question has given me mass, I need RFM there. Since if they give mass, find RFM. Carbon dioxide is 12 plus 16 times 2, which gives us 44. Now, understand that this RFM is for 1 mole, Avogadro's number is for 1 mole, so we can relate these ones. So 44 grams of carbon dioxide contains 6.02 times 10 to power 23 molecules. The question is talking about molecules here. So 0.88 grams of carbon dioxide contains, we could multiply here, 0.88 times this value. Then we are dividing it right away by the 44 molecules. So this right away gives us, punch into your calculator, 6.02 exponent 23 times 0.88 divided by 44. This gives us 1.204 10 power 23 22 molecules here. So you can pass by also the other alternative method. You can use the other alternative method of first finding the moles that are formed in this, then recognize that one mole will have this, what of the moles you have got will have one. That's how now you can do it the other way around. Let's look at number 3. Find the mass contained in these ions of sodium hydroxide. Ions of sodium hydroxide. So let's look at how many sodium ions and hydroxide ions are actually being counted in that compound. So let me limit it probably to hydroxide ions for one type of ions in this question of hydroxide ions. So then oxygen is 16, hydrogen is 1. Let's dive into that. Find the mass in these ions. But if they give you the number of particles, make sure you relate it to Avogadro's number. So now, if we know Avogadro's number, Avogadro's constant or number is actually 6.02 times 10 power 23. Now there will be ions because the question is in terms of ions. So they have given you ions, and also this is for ions, they want the mass. So I need the RFM. Since they want the mass, I need the RFM of hydroxide ions first. RFM of OH ions this is 16 plus 1, giving us 17. Now 17, we agree that this 17 is for 1 mole, and this 17 is also for the Avogadro's number, because Avogadro's is for 1 mole, this is for 1 mole. Instead of getting moles to spend a lot of longer route, I would first get RFM related to this. Since they have given me ions, and already I have also ions here, so these ions here will actually weigh this, what of this will weigh what, and that's how you relate it to. That's how you rate the Avogadro's number. It's normally used to answer questions relating to number of ions, molecules, or atoms, and finding them, or finding some parameter given the ions or molecules. So here I'm going to say this value weighs that mass 6.02 times 10 power 23 ions weighs, so it will weigh 17 grams of hydroxide ions. Hydroxide ions. 123.01 times 10 power 23. You start with what you have. I wouldn't start with 17 since I'm looking for mass. So weights, you just cross multiply 17 times 3.01 times 10 power 23. Divide, this time was this out of that. 0.02, 23 grams of OH ions. So let's punch in that value. That will be right away, 17 times 3.01 exponent 23. Always, there are many terms, keep them in brackets. So we are dividing by 6.02 exponent 23. This is 15, sorry. This is 15. 23. So let me adjust that one. 15. That's 15. So that's 15 there. Gives us 8.5 times 10 power negative 8 grams of OH ions. Hydroxide ions. That's how you answer that. So let's dive into the next subtopic. They are called stoichiometry in terms of masses. So stoichiometry in terms of masses. Stoichiometry. Now, stoichiometry is a concept, or it is the way we relate reactants and products through a chemical equation. Rather, calculating can simplify it as calculating amounts of reactants and products using well-balanced equations, or the way the amount of products and reactants are related by a well-balanced equation. So you look at how much products are there, how much reactants are there by a well-balanced equation. So let's have here two examples here. Lead to nitrate decomposed let's have it discussed well here. In this also, put two questions, then we shall be right to go. So, question 1, when 4.66 grams of lithium nitrates were heated strongly, they decompose according to the equation. And now this with nitrate composed down. Calculates the mass of nitrogen lead is 207, nitrogen 16, oxygen, nitrogen 14, oxygen 16. Now the question goes, we are going to relate reactants to the products using this equation, then we calculate for the masses. Let's read the question together. You can try it, pause the video, feel free to try it, then continue the video. When 4.66 grams of lithium nitrate were heated strongly, they decomposed according to the equation. Calculate the mass of the residue. Now, whenever you heat a solid substance, what remains down in the boiling tube or test tube is called the residue. The gases nitrogen dioxide and oxygen dioxide will have escaped over. So let's punch in that question. Now, when you calculate the mass of the residue, now the residue is lead to oxide, but remember the question gave you the mass of lead to nitrate. So we are going to relate lead to nitrate whose mass is given and lead to oxide whose mass is required. So you get both of their relative formula masses. RFN of lead to nitrate, that gives you lead is 207 plus nitrogen is 14 times 2 plus 16 times 3 times 2. This right I give 331. Can you? Okay, 331 there. Now let's also get the RFM of lead to oxide that is 207 plus 16 gives us 223. So that is 223. Now we are going to relate 2 moles, produce 2 moles of lead to oxide. So 2 moles of lead to nitrate, can use the full one but I don't have space, produces 2 moles of the residue of lead 2 oxide. So now we bring in these masses, 2 times the RFM of lead, that's 331, the nitrate of PB nitrates produces, now it will be 2 times for this, 223 grams of lead 2 oxide. What of the mass given in the question here? You can go to a step of 1 gram, but that would be wasted of time. PB nitrates produces, just cross multiply, this value is 446, 2 times this, 446 times this, 66 divided by this is 662 grams. So it's punching that value, the formula, that is 446. 446 times 4.66 divided by 662 gives us about 3.14 grams. Just consider this decimal places to 2, so I've rounded to 2 decimal place here also. So that's the RFM of the residue. Now the question was like this. Carbon monoxide reduces carbon monoxide. We try this number on this other page here. Carbon monoxide reduces iron free oxide according to the equation. So iron free oxide plus carbon monoxide plus iron carbon dioxide determine the mass of iron free oxide required to produce 4 grams of iron. Iron is 56, oxygen 16 grams, 16. So how do we attempt that question? Of course, the question there in that question, we are simply relating 2 things. Coming the mass of iron 3, which is this, required to produce iron, which is this. So I'm going to relate this to this. So how do we arrive at that? We simply get the RFM of this iron 3 oxide. So RFM of iron 3 oxide is 56 times 2 plus 16 times 3. Let's punch in there the question. 56 times 2 plus 16 times 3. That gives us about 160. So, since the side being required is this one, I start with the other side. Don't start with this one because I have given this. I'm given 4 grams of iron. So I'll say 2 moles of iron are produced by 1 mole of iron free oxide. 2 moles of iron are produced by 1 mole of iron 3 oxide. I hope you see that. Then I would come here and say my atomic mass for iron is actually 56. So 56 times 2 grams of iron are produced by still 1 now times for iron fluid is 160 grams of iron 3 oxide. What of this mass given as 4 grams of iron? So 4 grams of iron are produced by, let's multiply 4 times 160 divided by 256 times 2 is 112 grams of iron 3 oxide. Okay, let's punch in there. So that is that's about 5.714. But then let me round to a whole number, because the question already gave me a whole number here. So it would be better representative of the question. Let's now look at, this is how we use stoichiometry to get the masses. So let's look at now volumes of gases as our last discussion for this topic here. So how do we get volumes of gases? Now, for gases, normally whenever we are measuring gases, we start by measuring their volumes. Of course, we can also get the mass of the gas. So we can also get the mass of the gas, but preferably gases are expressed in volumes of gases. Now, gases have fixed volumes at standard conditions. There are two standard conditions. So there is what we call a molar gas volume. Is the volume occupied by 1 mole of the gas at standard conditions. And there are two standard conditions here to measure volumes of the gas, or what we call standard temperature and pressure, or room temperature and pressure. So 1 mole of the gas occupies 22.4 liters, which is equivalent to 22.4 dm3, which on converting is equivalent to 22,400 cm3 or mils at STP, at standard temperature and pressure. STP, standard temperature and pressure. Then also 1 mole of the gas, standard volume again is this one, occupies 24 decimeters cubed, which is 24 liters, which is also 24,000 cubic centimeters at RTP. So at standard conditions called room temperature and pressure, at room temperature and pressure, the gas uses 24. 1 mole of a gas, of course I told you 1 mole of any substance is equivalent to its RFM. So if carbon dioxide is, we are taking it to be 1 mole, in fact we can say 44 grams of carbon dioxide, which is 1 mole, also occupies this. So a certain mass that can fit in 24 decimeters cubed is what we are calling 1 mole of it, which is actually occupying the volume at room temperature. So under standard temperature and pressure, we use this value. Under room temperature conditions, we use this value. So these are values used to obtain, to relate volumes of gases with their masses and with their moles. So let's relate and do some numbers here. Let me dive into 3 questions here. Then also engage in stoichiometry in looking for volume. So question 1 here. So have this at your attention that at STP, 1 mole of the gas is 22.4 dm cubed, which is the same all through here. At RTP, 1 mole of the gas is actually 24, all these other volumes. Let me now go into about 3 questions here. Or rather, I can go into about 2 questions, then we go to stoichiometry here. So question 1, calculate the volume, the volume of calculate the volume of 6.4 grams of sulfur dioxide at RTP. Now sulfur 32, oxygen is 16, and 1 mole occupies 24 dm cubed at RTP. So there are conditions. Let me dive into a question here. How many moles of carbon dioxide can be found in 88 can be found in 44.8 cubic centimeters of the container. Okay, so molar volume, because that is pretty just direct, you will know the molar volume container at STP. So let me give you the last question here. Find the mass of oxygen find the mass of oxygen in 96 decimeters cubed of the container at RTP. Let's dive into that. Let me do these 3 questions, then turn down to stoichiometry. Hope you are paying attention. You can pause the video, try them out and compare with this. Now calculate the volume of 6.4 grams of sulfur dioxide. Now since the question has given us mass, right, I will find the RFM there. So RFM of sulfur dioxide, that gives me 32 plus 16 times 2, it's about 64. Now we know 64 contains 1 mole, and also 1 mole occupies that. So we are going to say 64 is actually equivalent to that value. 64 grams of sulfur dioxide occupies 24 dm cubed. Out of 6.4 grams of sulfur dioxide occupies, we cross multiply 6.4 times 24 out of 64 dm cubed, which is, so the punch in that is 6.4 times 24 divided by 64, that gives us 2.4 decimeters cubed. So you wouldn't have started with saying 24 has this. We will start with what we have. We have the mass, so we use the RFM here to check and understand that the RFM is for 1 mole, this value is for 1 mole, so this RFM would occupy that. What of the mass given would be occupying what? So I think that's pretty easy. Let's dive into this. How many moles of carbon dioxide are found in this? Noticing that the molar volume at STP actually has 1 mole. So 1 mole is for the molar volume at STP, which is 22.4. So, but they are giving us the 1 mole, so I will later say 400 cubic centimeters contains 1 mole of carbon dioxide. I hope you understand. You say already this STP volume is for 1 mole of the gas here. I can't say 1 mole occupies this because they have already given me volume. So you start with what they have given me. If they give you volume, start with volume. So I will say now out of 44, find these cubic centimeters contains 1 times, we cross multiply this time with that 1 divided by this. 400 moles of carbon dioxide. Punch in there in your calculator. That's 44.8 divided by 400 there. So that gives us 2 times 10 exponent negative 3 moles, or which is 0.030, 0.0, that 3 zeros there, so 2 moles. Because this is 1, 2, 3. So that's how you get moles from there. Let's do the last one. Here then we go to stoichiometry. This one number can't be enough for us. So find the mass of oxygen in 96 decimeters of the container at RTP. The question wants mass, so I need RFM. Hope you understand there. RFM of oxygen is 16 times 2 because each oxygen atom is 16. So it is 32. So this 32 of course has 1 mole. And also, since it's for 1 mole, it would occupy the volume at RTP, which is 24. So, I'm now going to say, since I need mass, I can't start with mass. So, we start with 24 decimeter cubed contains 32 grams of oxygen. This is for 1 mole, this is for 1 mole, so they are related. Then 96 decimeters cubed contains 32 times 96 out of 24 grams of oxygen, which is, so we multiply the 32 times 96 divided by 24. That gives us about 128 grams of oxygen. So that's how you arrive at those calculations. Allow me to discuss stoichiometry in getting volumes of gases here. So clear this. Stoichiometry in getting volumes of gases. So stoichiometry involves using chemical equations to obtain what you want. So stoichiometry in volumes of gases. Stoichiometry in volume of gases. So let's do 2 numbers here. And the first question would be that and this is magnesium reacts with nitrogen according to the equation. So that is magnesium plus nitrogen gives us magnesium nitride. This is 3. Calculate the volume of nitrogen that reacted that produced 4.5 grams of magnesium nitride. So magnesium is 24, nitrogen is 14. So let's have answer question 15. Number 2. When calcium nitrate was heated strongly, the total volume of the gaseous products was 5.52 decimeters cubed at STP. Determine its calcium nitrate determine the mass of calcium nitrate that decomposed. So calcium is 4, oxygen 16, nitrogen 12. One more of the gas occupies 20.4 liters. That's at STP. Here, molar gas volume is 24 dm cubed at RTP. Let's do those two questions and we can have that topic concluded about them. So, magnesium reacts with nitrogen according to this equation. Calculate the volume of nitrogen that produced this of magnesium nitride. Magnesium nitride is this. So, let's look for its RFM since they have given already its mass. If they give you mass, first find RFM. So RFM of magnesium nitride is 23 times, that's 24 for magnesium, 24 times 3 plus 14 times 2, which is equal to, that is 23 times 24 times 3 plus 14 times 2 gives us 100 here. Now look here, they want the volume of nitrogen, so they want this to be related to this. So the first step we are going to acknowledge is that one, since you are given mass, we shall start with the one whom we are given to calculate the one whom we don't have. They gave us mass of magnesium nitride, so I have to state 1 mole of magnesium nitride is produced by 1 mole of nitrogen. So 1 mole of magnesium nitride using symbol form is produced by 1 mole of nitrogen. Then I'm now bringing this mass of nitrogen. 1 times 100 grams of magnesium nitride is produced by, now for the case of the gas, since we're interested in volume, it's 1 mole actually corresponding to 24, it's 1 mole decimeters cubed of nitrogen. Then what of this mass given in the question, 4.5 grams of magnesium nitride is produced by cross multiplier, that's 24 times 4.5 divided by 100 here. So decimeters cubed. So we punch in that, so that is 24 times 4.5 divided by 100. That is giving us about 1.08 decimeters cubed of nitrogen. That's how you obtain the volume of that gas there. Let's look at this question next, number 2. When calcium nitrate was heated strongly, the total volume of the gaseous products was this, at STP rather. Now, They are talking about total volume of the gas. There are two gases. So we are going to relate the two. Determine the mass of calcium nitrate. So we are also looking at this part. Since they want its mass, I have looked for the RFM of calcium nitrate. So RFM of calcium nitrate, since they wanted its mass, that is 40 plus 14 times 2, 16 times 3 times 2. So 40 plus 14 times 2, 16 times 3 times 2. 40 plus this plus this at 164. Of our quantitating right there. Now, since we are interested in this total, we're going to look at the total moles of about 4 plus 1, that is 5 moles. 4 on this, 1 on this. So, since they want mass and they gave me volume, I will have to start with the side given. So, I'll have to start with this side, that's 5. 5 moles of the gases are produced by 2 moles of calcium nitrate. Let me shift it up here. Since down there is not very visible, let's shift it up there. So we are going to multiply 5 times 4 because gases always occupy that STP volume, each 1 mole of the gas. So for gases, we are going to replace them with this. So 5 times 22.4 decimeters cubed of gases are produced by, so for this case, we multiply 2 times this mass here, times 164 grams of calcium nitrate. So now the next step is this 5.52 decimeters cubed of gases are produced by, so this is 5.52 times, now this 2 times 164 times 164 would be 328 divided by 5 times 22.4, that's about 112 grams, which is, so we punch in there 5.52 times 328 divided by 112, that gives us 16, which is 16.1. They have rounded this to 2, so let me just maintain it to the small places, grams of calcium nitrate. That's how you handle mole concept. Thank you for viewing. And never do this exercise. Please subscribe this YouTube channel and wait for more simplified videos in chemistry. Bye.